safety factor, so n is going to be equal to sigma m prime plus 155.88 divided by the ultimate tensile strength, which is 560, plus sigma a prime, which was 175, divided by the endurance limit, which you normally would calculate, but now in our case is given, 280, and that needs to be raised to the power minus 1. And so you find that is 1.11. So now we're going to calculate the Gerber parabola. Would you expect a smaller safety factor than the Goodman line or a larger safety factor? Larger, right? Because it is a less conservative failure criterion, so you'd expect that it will give you a larger sense of safety, and that will be translated in a larger safety factor against fatigue failure. So for the Gerber parabola, we got n times sigma m prime. Let's fill in the numbers. I mean, the equation is right there. So n times sigma m prime is 155.88 divided by sigma ut, which is 560 squared. And then we got n times sigma a prime, 175 divided by sigma e, which was 280. Minus 1 is equal to 0. And so then you can solve for n. And so you find that you're obviously going to find two solutions. The first one is minus 9.37, and the second one is 1.36. Obviously the first one does not make sense. You can't get a negative safety factor. This is a trivial solution. And so this is the one that is a true solution. Is this clear to everyone?
So we usually define a sigma e with a certain number of like I can't think of the word right now, like a certain number of like trials or iterations again.
Cycles?
Yes, cycles. That's what it's looking for.
Now, sigma e is always for infinite cycles.
Oh, right. Yeah.
Sigma f is for a number of cycles.
Right. Yeah. Okay, that makes sense.
Yes.
Can you explain why that safety factor is higher? Because to me it seems like it's less conservative and lower safety.
No, you would have a higher safety factor, right? If it's less conservative, you get a higher safety factor because you get a false sense of safety, if you will, because it's less conservative. False is not the right word because obviously based on experimental data, it's actually more accurate, right? But the more conservative for the same loading condition, the lower safety factor you get. Yes?
It seems that the Gerber parabola goes through the sample dots, all the dots. That means some samples did fail, some samples would fail in the Gerber parabola.
Yeah, but that's not the right way to think about it, right? So fatigue is a statistical phenomenon, right? So each data point here is also the average of a number of data points that were made at exactly this configuration of sigma a prime and sigma m prime. Right? So this is all based on averages and based on multiple repeats of those experiments, and then you get a cloud of data, and then you do a best fit through it. None of these criteria, by the way, and this is true for all failure criteria, if you get a safety factor of 1, that doesn't mean you have absolute certainty it's not going to fail, right? Because none of these failure criteria are derived from first principles. They are all sort of like our best guess for a particular loading situation, a particular type of material for when failure occurs. Because there is no unifying theory that says this is when failure occurs under compliance. This is sort of like the best we can do. And so you have to interpret it that way too.
Yes, thank you.
Other questions? So this is the end of part 7. And I know we have, and like I said last time, if you feel like we haven't practiced fatigue failure enough, that's true. But the next part is all going to be about example problems on this type of stuff. So this is all of the theory that we're going to talk about for fatigue failure. And we're now going to learn how to apply that to design of shafts, right? So what we did in this part is we talked about alternating stress, we talked about fluctuating stress, and we talked about fatigue failure for infinite life and fatigue failure for finite life. Finite life, I mean, I guess that's kind of a funny term, but for a finite number of cycles, okay? An infinite number of cycles. So those are sort of the things that these are the things that we covered in this part. And now what we're going to do is we're going to apply that to design of shafts, which is going to be our part 8 of the course. And like I said, we're not going to cover any new material. The only reason why we dedicate a separate part of the course to design of shafts is because it's by and large the most common mechanical element that is used in machinery. For that reason, we want to pay some particular attention to it, and in addition, it allows us to practice these fatigue failure criteria in way more examples than we currently have done, because I understand that if you see this the first time, this may not be that clear. When I was a student and I saw this for the first time, I was kind of confused about that too, and it took a while for me to get familiarized with those calculations. And so what we're going to do now is I'm going to give you a little bit of tips qualitatively about shaft design. How do you think about shaft design, qualitatively? Then we'll go through a recipe of the mechanics of doing calculations, and then we'll focus for several lectures on just doing example problems on shafts, both static loading and fatigue loading. Okay? So that's the plan. So what is a shaft? A shaft is a rotating mechanical element. Although rotating, you can have stationary shafts too, actually. So, but I'm going to write rotating. Rotating mechanical element. Used to transmit power or motion. The reason why I say it's non-rotating is actually my PhD advisor once told me the story that he was deposed as an expert witness in a case. He was deposed for 5 hours about the difference between a shaft and a spindle. So this was a patent infringement type of thing, right? And so the lawyers wanted to know the exact difference between a shaft and a spindle. And he says a spindle implies that it's rotating, and a shaft doesn't necessarily imply that it rotates, which I agree with. But the definition in Shigley says, shafts are being used to transmit power or motion, and you can't do that with a stationary shaft. I guess unless it's a cantilever beam, maybe that would be considered transmitting motion still. But anyway, those are minutiae. We could say it's a rotating mechanical element that is used to transmit power or motion. So how do we think about designing a shaft? There's two things about shaft design, right? Two things. There is stress. Stress calculations, which is local. What I mean by that is you could locally, at each point in the shaft, calculate the mechanical stress. It's not a global measure of that shaft. The other component that is important is deflection, and that is a global measure. It depends on the entire shaft. While stress depends on the local loading at that point of your shaft. And so you will typically for that reason, you will typically start your shaft design in this order. You will first find out what is the external loading that is going to act on my shaft at each point, and I'm locally going to design my shaft such that the dimensions are thick enough that it can withstand that load without deforming. And then, after you've done that local design and put it all together, you're going to check whether the deflection meets your requirements. If it deflects too much, you're going to have to do something. Right? Intuitively, what could you do if your shaft deflects too much? Make it bigger, or? That's a common misconception. So deflection is, kind of inverse proportional to typically a term that looks like this, EI, right? Where E is your Young's modulus, and I is your moment of inertia of the cross-section of your shaft. If you look at those formulas in your formula sheet for shafts that are supported in 2 supports or cantilever beams or whatnot, there's always the term 1 over EI. We call it the bending stiffness, right? Where E is the Young's modulus of the material and I is the moment of inertia. And so indeed, if your deflection is too large, you could work with these 2 terms to reduce your deflection. And so you could pick another material that has a higher Young's modulus to do that, because if you increase E, then this fraction is going to decrease and your deflection is going to decrease. But most shafts are made of steels, or some steel alloy, right? And the Young's modulus of all steel alloys is almost constant, right? As a stainless steel versus a carbon steel, the Young's modulus is always going to be around 200 to 210 gigapascals. So changing the material, if you stay within steels, is not going to affect this term very much. Now, if you go from aluminum or titanium to steel, yes, aluminum is 80 gigapascal, titanium is 115 gigapascal, so that is a factor 2 with your steel. But by and large, the biggest impact term is this I, right? So changing the moment of inertia by changing the cross-section or the shape of the cross-section could reduce your deflection by way more than choosing a different material. So remember that. Your material is a very limiting factor. In fact, you see that also with bicycles, right? I mean, I don't know whether you guys remember the time when bicycles were made out of steel, the frame. And then they from steel, they went to aluminum bicycle frames. And with that change, the tubes of the frame also dramatically increased in size. You get these what they call teardrop-shaped tubes and stuff. The reason for that is this, right? You went from a modulus of elasticity, Young's modulus of 210 gigapascal from steel down to aluminum, which is 80. So these frames would deflect way more if you keep the same cross-section of tubes. And so they had to increase the moment of inertia. They did that by making them bigger. And today you see that too. Today there are not a lot of steel or aluminum bikes anymore. They're all carbon fiber. And for those carbon fiber frames too, those tubes are oversized in diameter. And the reason is because you've got to have a large moment of inertia to reduce deflection. Okay. Shaft layout. That's also something to consider. Shafts are typically in this stepped formation, designed in this stepped formation. The reason for that is because, well, the stress varies throughout the shaft. You want to minimize the amount of material that you have to use. Let's say this could be a typical shaft shape here. And then supported in 2 bearings here. But these stepped features are also oftentimes used to seat other mechanical elements. Right? What if you need to have your shaft withstand an axial thrust load or something? Then you could have that element sit here, and this step, this collar essentially, is going to be able to resist an axial load because it's solid. Another reason is just for positional seating. If you need a pulley, you could put a pulley here, and by making it flush with these step features, you right away have it in position, and it doesn't move around on your shaft. So it's both in terms of loading and positional fixation, you can use your shaft layout to accomplish those goals. Rotating mechanical element used to transmit power or motion, that means that we're applying a torque to our shaft. And so torque transmission becomes an important thing. And there are many ways that a shaft can transmit torque. Right? You have your belt pulley, you have gears. Right? If you have two gears on two parallel shafts, essentially what that does is, or you have a motor, for instance, with a gear that drives a gear on a shaft, that motor is essentially applying a tangential load to your shaft, and that tangential load, together with the leverage arm, creates a torque moment that makes the shaft rotate, right? So there's a bunch of ways that this can be done. I mean, you can have keys, you get splines. There's a myriad of opportunities there, or methods of doing that. We're going to focus on two types so that we can narrow it down a little bit, again, in the interest of time. And I'm going to take two common ways that torque is transmitted on a shaft, and we're going to briefly talk about that, and then all the following problems that we're going to solve are going to be one of those cases of torque transmission. But the concepts of actually calculating the shaft, of course, don't change. They're independent of the torque transmission. This is just about how is the torque being applied to the shaft. The first method that we're going to use is what I call motor machine. What's the difference between a motor and a machine? Well, if this is a motor, and this is a machine that is being driven by a shaft driven by that motor. This is motor. This is machine. In the case of a motor, your torque moment, mt, is in the same direction than the rotation of the shaft. So mt and omega are in the same direction, okay? Same sense. Because I'm applying a torque moment and I'm making that shaft to rotate in the same direction. Now for a motor, that's not true. For a motor, if this is your rotational direction, omega, then your torque is in the opposite direction because your motor is essentially an inertia. Your machine essentially is an inertia that needs to be rotated by the motor. So it's essentially applying a resistance moment. It tries to not rotate due to the inertia, right? Is that clear to everyone? Okay.